GO600, a gravitational wave detector. In other words, a facility for discovering gravitational waves. They must exist, or at least that's what Albert Einstein concluded in his general theory of relativity. But we haven't yet been able to prove they exist, not even with GO600. Einstein taught us that gravitational waves distort space, so it should be easy to conduct a length measurement to prove they exist. The problem is that the change in length is too small. Up to now, we've only indirect evidence of the existence of gravitational waves through the energy loss that was observed for years in the double star system, PSR 1913+16. Gravitational waves, if they exist, must compress or stretch space-time. And it's precisely this compression or stretching that GO600 aims to measure. For this, laser beams are sent through the detector, and we measure whether the laser beams need more or less time to return to the starting point. The effect of gravitational waves on the measuring device depends on the size of the measuring device. Our apparatus, GO600, has 600-meter arms, which means we have to measure and register changes in length of a thousandth of a diameter of an atomic nucleus. Nowadays, we use laser interferometers for this. As far as we know, these are the only devices that can detect such tiny changes in length. It's clear that on Earth, the measurements we can conduct are limited, but not in space. That's why we are working on LISA, a laser interferometer space antenna. But why is it so important to prove the existence of gravitational waves? The major part of our world is dark. We know that 96% of the universe is made up of something we don't know, and of the remaining 4%, only about a tenth is lit. But everything is subject to gravity, so there's the hope we can also show everything in gravitational waves. In space, we have ideal conditions to measure these gravitational waves because nothing wobbles there, there's little interference there, and you get the arm lengths almost free of charge. Long measuring distances also play a decisive role in another application, in measuring the Earth's gravitational field. This is the task of the GRACE mission. GRACE stands for Gravity Recovery and Climate Experiment. GRACE consists of 2 satellites. The first satellite flies over an area of higher gravity and is accelerated by this. Sometime later, the same thing happens with the second satellite. For a very short time, the distance between the 2 satellites increases, if only by a hair's breadth. This is measured, sent back to the scientists on Earth and processed to obtain an image. Measuring the vertical profile of our Earth doesn't tell us directly if the masses have changed. If we really want to know if the groundwater has flowed away, or if the height of the surface has simply changed, then we have to measure the Earth's gravitational field and its temporal variation directly. And we can do that in such geodesy missions as GRACE Follow-On. And the development continues, with Quest as a key player. The federal government has now granted financial support for the GRACE Follow-On project. This means that high-precision measurement technology developed by Quest researchers will be sent on another space mission as early as 2016.